So thank you for your kind introduction. It's a great honor and pleasure to give a talk at this conference. My name is Yusuke Hama. I'm a research scientist at AIST, National Institute in Japan. And today, I would like to talk about an algorithm that we recently developed called Subsampling Factorization Machine Annealing. Okay. So this is the outline of my talk, and there are 5 parts. And in the first part, I would like to talk about the introduction, so the background, motivation, and goal of our research. In part 2, I would like to explain what, how do you use the laser pointer? This one? Top one, okay. So these 2 things, so black box optimization and factorization machine annealing are. And part 3 and part 4, they're going to be our research results. And in part 3, I would explain what this subsampling factorization machine annealing is. And in part 4, I would like to show you our numerical experimental results. And part 5 is going to be our conclusion and outlook. Okay, so introduction. So we have 2 motivations for our research, and the first one is the optimization, to tackle optimization problems in the real world. So as we all know, optimization problems are ubiquitous in science and engineering, and the examples of the basic optimization problems include max cut problem, traveling salesperson problem, and graph coloring problem. And by using like techniques to solve such basic problems, we are able to tackle the optimization problems in the real world. And examples of the optimization problems in the real world includes so logistics, production planning, and these are done by, for instance, automobile companies. Okay. And our second motivation is to develop 2 cutting-edge technologies. And the first one is quantum computing, so both annealing and gate-based quantum computing. So, yeah. And this second one is the machine learning or artificial intelligence. And these are the 2 considered to be the, expected to be the key ingredients to tackle real-world problems. And oops, I'm sorry. Okay, and this the research and development of both of these technologies, so quantum computing and machine learning, and it is expected to continue. So in our work, we're going to focus on the development of the algorithms, and by using these 2 technologies and tackle real problem. And our goal is to develop the optimization, develop the algorithms for solving optimization problems in the real world using quantum computing and machine learning. And here I would focus on the class of optimization problem called this black box optimization. Okay, and furthermore, we would like to aim to promote the next generation industry using these algorithms. Okay, so part 2. Okay, so here let me explain what this black box optimization is. And black box optimization is an optimization algorithm where an objective, mathematical form of objective function is unknown, and such objective function is expensive to evaluate. And oops, so this is the schematic of this black box function. And the question is how to solve such an optimization problem. And we're going to do this in the following way. So we are going to process these 3 steps sequentially and iteratively. So data generation, modeling data, and surrogate model optimization. And in the following, let me explain the role of each procedure, so step. So first, the data generation. So as name suggests, this is the process to collect the data of the target objective, the black box objective function. denoted by this large T, and this can be done, for instance, by performing experiments or running simulations. And second, the modeling data. And this is done by using this data set at hand and run some sort of machine learning algorithm and construct a model function. And and this model function is also called a surrogate model. And once this surrogate model has been constructed, we are going to run an optimizer and find the optimal solution to this surrogate model. So I'm going to denote this by X dagger. And once we find this X dagger, we're going to add a data set, X dagger, and the corresponding objective function value to the data set at hand. And we're going to repeat these three steps over and over. And as a result, we are able to augment the data set and find the optimal solution of the target objective black box function. And yeah, this is the working principle of black box optimization. And next, I would like to talk about this annealing-based black box optimization. So as I explained previously, so there are 3 steps to run this black box optimization. And in this scheme, we're going to choose this surrogate model to be this qubit functions, and correspondingly the optimizer to be the annealing methods such as simulated annealing and quantum annealing. And what I think the interesting thing about this this annealing scheme is that this is one of the examples of the hybrid technologies of quantum computing and machine learning. And next, let's delve deeper into this modeling data part. And recently, there's a class of machine learning model called factorization machine has been applied in this context. So this is the mathematical form of factorization machine. So W's and V's. So these are trainable parameters, and I'm going to call them FM models. FM parameters. And by comparing these two formulas, we see that the factorization machine is one of the qubit functions. And the main feature of this factorization machine is the coefficients of the quadratic terms. So, and this is represented by a hyperparameter, small k. And this indicates that, so to train this, the quadratic coefficients, this is going to be, we can do this with the computational cost in the order of k dot and bit. So this is the number of spins. And so by fine-tuning the value of this small k, we are able to train this model with the lower computational cost than this general qubit function, training general qubit function. So this is one of the big advantage of using factorization machine. And the combination of this factorization machine and annealing, this is called the factorization machine annealing. So Kikuchi-san talked about this yesterday. And it has been studied extensively from both fundamental and applied perspectives. However, there's a disadvantage, and that is, unlike the Bayesian optimization, the uncertainty of training these model parameters is not taken into account in this factorization machine annealing. So in our work, we would like to construct this FM-based algorithm by keeping this advantage while improving this disadvantage. And how can we do this? And to do this, let's revisit the basics of combinatorial optimization. And to solve this combinatorial optimization problems effectively, we need 2 core concepts. So the first one is exploration, and the second one is the exploitation. So the exploration is to search for the best candidate solutions, as many as possible. And the second one, the exploitation, this is to focus on finding the optimal solutions of the problem. So we can see that we can solve this combinatorial optimization problems effectively by first performing this exploitation in the first half of the optimization processes, while in the second half we perform this exploitation. So in terms of these two concepts, we can re-express that the factorization machine annealing is weak on this exploration performance. So we are going to create our algorithms by amplifying this exploration performance. And how are we going to do this? And the solution to our this problem is to run an algorithm called Subsampling Factorization Machine Annealing, SFMA. So here, let me explain what this SFMA is by using this schematic. Okay, so in the conventional method, FMA, we use full data sets to train the FM models. In contrast, in our scheme, we don't do this, and instead, we are going to use subdata sets sampled from this subdata sets to train the FM models. So what happens by doing this is that we are able to train the FM parameters or models probabilistically. And this means that the optimal solution to the FM models are found probabilistically. So in other words, we are able to generate, the fluctuation of this optimal solution is generated. So, and this is going to be the driving force to explore a wide range of binary solution space indicated by this figure. And this leads to the amplification of exploration performance. So in summary, to summarize these basic points, so first, so the main difference between our algorithm and the conventional method, FMA, is that in our scheme, we use the sample subdata sets instead of full data sets. And in this sense, we call our algorithm subsampling factorization machine annealing. And second, since the FM models are trained probabilistically, we are able to explore a wide range of the solution space, which leads to the amplification of exploration performance. Okay. And lastly, there's another main feature of this SFMA, and that is we can run this SFMA with the lower computational cost than the FMA. And this is because we are using the subdata sets to train the FM models. And this is done by controlling the value of parameter large R. So this large R means the ratio of this full data set size and the subdata set size. So from these characteristics, we expect that our algorithm SFMA enables us to find the optimal solutions with faster speed, higher accuracy, and lower computational cost. And we are going to verify this by carrying out the numerical experiments, our numerical experiments. Okay, so let me explain, demonstrate our numerical experiments. And first, so we are going to perform this experiment throughout this a class of problem called lossy compression of data matrices, or matrix factorization. And this is a technique to efficiently compress the data under consideration while keeping the relevant information. And this is, has been used in various fields such as image processing, audio recognition, and materials informatics. Okay, next, let me describe how to mathematically describe this lossy compression of data matrices. So we are going to decompose this matrix W, which represents the information under consideration, into a product of integer matrix large M and the real matrix large C. And here we assume that all the elements of large A take either -1 or 1. And by using this pseudo-inverse of M, we are going to eliminate this C and rewrite the right-hand side into this matrix large B defined in this way, and calculate the Frobenius norm between this target matrix large W and large V. So this is one. Okay. And so our goal is to find the optimal configuration of large M, which minimizes this Frobenius norm. And we are going to do this by regarding this problem as a black box optimization problem, where this Frobenius norm is a black box objective function. Okay. And lastly, the setup. So in our experiments, we are going to introduce 10 W matrices. So the problem instance for each spin numbers, 12, 16, and 20. And in our this talk, I will present the results for 12 and 20 spin cases. And for creating the subdataset, we use this uniform sampling. And according to these setups, we are going to perform the numerical experiments as benchmarking tests between our algorithm SFMA and the conventional method FMA. Okay, so this is our first result. So in our experiment, we calculated two types of quantities. So first one is the averaged optimal values yielded by the algorithms, so in A and E. Okay, and the second quantity is the success rates of finding the optimal solutions. So we plot this them in B and F. And please look at the red curves, okay? And so these are the results obtained by our algorithm, SFMA, by taking the hyperparameter to be 0.4. And first from these two plots, we see that our algorithm, SFMA, finds the reaches the optimal solution faster than any other algorithms. And correspondingly, in B and F, we observe that our algorithm shows the highest success rate. So as a result, we observe that our algorithms, SFMA, outperforms the conventional method, FMA. Okay. And so next, our second result. So in the previous slide, I showed the results where that the results that exhibits the theoretically expected behaviors clearly. However, in some problem instances, SFMA shows poor performance, and we try to improve this performance by increasing the iteration number of BB black box optimization, and this lowering the hyperparameter value of hyperparameter large R. And we did this in two ways. So first one is we extended the iteration number from 2n squared to 6n squared, while we lowered the value from 0.4 to the 0.1. And in the second way, we ran two SFMA with two parameter settings. So first, we ran the SFMA with taking the iteration number to be n bit squared and R 0.1. And the second part, 5n squared with 0.01, which is 10 times smaller than the first R value. And the results of these two algorithms are plotted in pink and purple curves. So from these two plots, we clearly observe that that these two algorithms exhibit significantly the higher performance. So both in this average value and success rates, so speed and accuracy. And we interpret these results in the following way. So we took the value of R to be corresponding small. And as a result, the exploration performance gets further amplified because by taking lower R, the fluctuation becomes larger, and as a result, the exploration performance gets got amplified. So this means that we are able to run the SFMA by so according to the problem size, by taking corresponding small r, we are able to run this SFMA by with the lower computational cost and the high success rate. So I consider that this is the indication of the scalability of SFMA. Okay, so finally, our third result. So in the two previous slides, I showed you the results of the SA, so simulated annealing. And we also performed the computation using this running quantum annealing. And the red curves are the results of SA, and the light blue curves are the results of quantum annealing. And in our experiment, we did not observe the clear quantum advantage. However, for instance, for like larger scale problems or refining the quantum annealing schedule or redesigning the Hamiltonian quantum annealing, we expected that we observed the clear quantum advantages, and we would like to explore these themes in our future work. Okay, so summary. So we verified that that our algorithm SFMA outperforms FMA in both speed and accuracy, and by taking corresponding low R, we succeeded in observing the potential scalability of our algorithm SFMA. And these are our future works. So yeah, thank you so much. Thank you for your attention.
I think we have time for one or two shorter questions. Are there any? If not, I have one actually. So basically, with the hyperparameter R that introduces how many or what fraction of your data points you use, I guess you, in some sense, introduce some uncertainty to your optimization problem with this R. So I assume you optimized over the optimal value or to find the optimal value of R for a specific optimization problem?
It highly depends on the problem. So that's like our other future work that we would like to challenge and
And actually, I was wondering if it might make sense to, because in some sense, now you can anneal this value of R, right? Start with a small r, so you get lots of fluctuations, and then change it over time and to get more specific, maybe, or?
So we didn't change the value of R in our experiment, but you can also do that.
Right.
Yeah, and I'm not sure which works better, but yeah.
Right. It would be interesting to see.
Yeah, thank you.
Right. Right. Then
So do you have any intuition why in this problem there is no advantage for quantum annealing? Do you have an intuition, or I don't know?
You mean intuition?
Yes, intuition. Or why you don't see a slight, even a small advantage?
So that's the thing that I want to know, and I don't know. So for instance, so by so taking like higher values of the parameters like numerics, maybe it's possible to amplify the performance, right? But just a bit, probably. Yeah, or yeah.
I think there was one more hand out. If it's a short question, I think we can still put it in.
Who was it? Thank you for your nice talk. And by conducting subsampling strategy, the data set becomes small. The number of data sets is small. So it has a possibility to get overfitting. So did you check the test error and training error?
So I think using the larger data set tends to show the overfitting. I think, isn't it the opposite? Because we're using the smaller size of data sets, so Do you understand?
Yeah. Okay. So it has no risk to get overfitting.
So okay. So how do you say? So it's quite different from it's different from supervised learning, right? Because this is not, the task is not to predict the output value of the new input data, right? It's to find the optimal solution of like the target, objective function. So we're just using the machine learning algorithm, but it's not to do the regression. So do you understand? Yeah.
Okay. Thank you.
Yeah.
And it's thank you, Yusuke, again.